Welcome back to the Deep Dive. This is where we grab a stack of expert sources, we drill down past the surface, and really try to extract that high-octane knowledge you need. Today, we are immersing ourselves in the world of industrial air compression engineering. And look, this isn't glamorous, but it is absolutely essential.
It's the hidden power source. It really is. Air compressors are the foundation for massive industries.
Like what, specifically?
Think construction, food processing, pharmaceuticals, manufacturing. I mean, when these machines fail, the ripple effect is immense.
So an engineer in this field isn't just fixing a machine.
No, not at all. They are maintaining the entire industrial backbone.
And our mission today is to use a very specific, highly targeted set of materials. We have 6 critical interview questions here designed for a high-level air compressor engineer. We're going to use them as a roadmap to mastery. These questions, they really distill the core technical knowledge and problem-solving skills.
Exactly. They separate an average technician from a truly essential professional. We're going to systematically extract what you need to know. Right.
So this deep dive is going to focus on 3 things: foundational knowledge of the equipment, the critical preventative strategies that ensure uptime, and, the troubleshooting mindset you need when a multi-million-dollar system suddenly goes offline.
Okay, let's unpack this immediately. Let's start with that foundational knowledge. The very first question in our source material is basically a gatekeeper question. Asks, what types of air compressors have you worked with? This isn't about rote memory, is it? It's about demonstrating a breadth of practical, hands-on experience.
That's right, because these 3 core types of compressors, they operate on fundamentally different principles. If you only know one, you only know a fraction of the field.
So you need experience across that whole matrix.
Yes, the function application matrix.
Sure.
A strong engineer needs to have seen it all.
Let's break down those core 3 then. First, the reciprocating compressor.
Right, so the reciprocating compressor is a positive displacement machine. You'll often hear it called a piston compressor.
A piston compressor, okay. And it excels at high pressure, but lower volume applications. It's very reliable, but it often requires more maintenance.
Because of the piston motion. The mechanical wear.
Exactly. You've got it. Think of it as the heavy-duty jackhammer of compressors, when you just need pure concentrated pressure.
Then we get to what you called the workhorse of industrial facilities, the rotary screw compressor.
Yeah, rotary screws are really the industrial standard. They provide a continuous flow and are just highly efficient in those medium pressure, high volume scenarios.
How do they work?
They operate with 2 rotors that mesh together, trapping air and reducing its volume. Their popularity really stems from their relatively simple continuous motion.
And less maintenance than the piston types?
Far less.
And finally, the third one, the centrifugal compressor.
This is where we move from positive displacement to dynamic compression. It's a different beast entirely.
Okay.
Centrifugal compressors use kinetic energy, a high-speed impeller, to accelerate the air, and then they convert that velocity into pressure. They are designed for massive air requirements.
So we're talking big industrial processes.
Huge. Steel mills, power generation plants. Seeing all 3 on a resume, that signals a really solid understanding of how varied industrial needs translate into specific equipment choices.
That makes perfect sense. So once an engineer knows which machine they're dealing with, the focus has to shift to optimization.
Let's jump to question 3 from our source. It singles out one specific component as crucial for operational health: the air-to-fuel ratio. Why does this simple ratio demand such high-level attention?
Well, what's so fascinating here is that the air-to-fuel ratio isn't really a mechanical fix. It's a thermodynamic balancing act.
A balancing act.
It dictates the efficiency, the emissions, and critically, the long-term health of the internal components. We're talking about maximizing combustion to generate power, while at the same time minimizing thermal stress.
So what happens if that ratio is off? Give us the technical breakdown.
Okay, so if the system runs rich, that's too much fuel relative to air, you get incomplete combustion.
Which means? It means heavy carbon buildup, it means fouling of spark plugs and much higher emissions. You waste fuel, and you significantly increase your maintenance cycles.
And what if it runs lean? Too much air.
That is often worse for the machine itself. Running lean increases the combustion temperature dramatically.
Oh, I see.
You risk overheating the entire system, damaging the valves, and potentially leading to premature wear or even catastrophic failure of seals and gaskets, all from that excessive thermal stress.
So the ability to monitor and maintain that perfect ratio isn't just about saving money on fuel. It's about preventing the whole thing from melting down.
You got it. It's about preventing catastrophic internal damage.
How is this actually managed in a modern system then?
Engineers rely on specialized equipment. They're often using lambda sensors or, sophisticated exhaust gas analysis to get continuous feedback.
So it's not a one-time fix.
Not at all. The best professionals understand that setting the ratio isn't a set it and forget it thing. It requires constant monitoring, constant micro-adjustments based on load, ambient temperature, fuel quality. It's a core preventative measure baked into every single operational hour. And that leads us directly from foundational principles to that preventative mindset.
Right.
High-level engineering is all about anticipating failure. Question 2 from our source asks, how do you ensure the efficiency and reliability of an air compressor system?
Okay, so this moves us into the specific actionable maintenance tasks. The source provides a pretty rigorous checklist, which proves that reliability is, well, it's earned through a repeatable process, not just luck.
Absolutely. Let's look at the critical 4. First, checking and replacing filters.
Sounds simple.
It sounds simple, but a clogged intake filter dramatically increases the workload on the motor. It reduces volumetric efficiency, and it can definitely cause overheating.
Okay, second on the list, monitoring oil levels. Now, why is oil quality and level so critical beyond just lubrication?
Great question. For a rotary screw unit, the oil doesn't just lubricate. It seals the rotors and it absorbs a significant amount of heat.
So it's a coolant too.
It's a coolant and a sealant. So if the oil level drops or the quality degrades, say from water contamination or just heat breaking down the viscosity, the system risks metal-on-metal contact.
And that would be catastrophic.
Leads to rapid component destruction. Diligent monitoring is absolutely non-negotiable.
Third, inspecting hoses and connections for leaks. Leaks are sort of the silent killer of efficiency, aren't they?
They are massive operational drains, just a huge waste. Even a small leak can account for a huge percentage of wasted power over time.
So how do you find them?
A professional inspection involves using acoustic detection or even soapy water tests, methods that go way beyond just a visual check to make sure the system is truly airtight.
And the fourth item on this checklist is ensuring the compressor always operates within its specified parameters. Yeah. That's where technology really steps in.
Correct. This is where you see the shift from reactive repair to proactive system management. We move into diagnostics.
Okay.
High-level engineers strategically use diagnostic tools, specifically vibration analysis and thermal imaging, to detect potential issues way, way early.
Can you elaborate on those? What are they looking for with those tools?
Certainly. Thermal imaging detects hotspots. That's an early indicator of friction or electrical issues or inadequate cooling, often weeks before a failure.
And vibration analysis.
With vibration analysis, you're using accelerometers to detect really subtle changes in bearing condition, rotor balance, or coupling alignment. If that standard vibration profile starts to change, even a little, you can schedule maintenance before the component reaches its physical breaking point.
That makes reliability not a hope, but a calculated certainty. But is there a risk of becoming over-reliant on these tools? I mean, can too much diagnosis slow down a fix?
That's a very sharp question. The key is integration. The tools should inform a maintenance schedule. They shouldn't replace human judgment. If a thermal scan shows a minor abnormality, the engineer uses that data to schedule an inspection during a planned downtime. But if a critical safety alarm triggers, that engineer has to immediately use their experience to bypass non-essential checks and focus on the fastest route to getting it back online.
So the tools guide the process, but the professional owns the decision.
The professional always owns the ultimate decision.
So if all those preventative steps we just outlined fail, how does an engineer pivot to active troubleshooting? That brings us perfectly to Section 3, where we can contrast the easy fix with the much more difficult diagnosis. Let's start with that immediate frequent issue. Systematic, low-pressure troubleshooting.
Right.
The machine isn't delivering. How does a professional methodically find the root cause?
Low pressure is often the most reported symptom, but it can have so many different causes. The approach has to be systematic to eliminate those common points of failure quickly.
And the data backs that up.
Oh, yeah. Based on historical data, studies suggest something like 70% of low-pressure issues are resolved just by checking the air inlet or locating a simple leak.
So we follow the source's clean 4-part checklist. Step 1, start by checking the air intake filter and any obstructions in the intake valve.
It's logical. If the machine can't breathe, it can't compress. Step 2 is to inspect the discharge valve. It might be stuck open or partially closed.
Which would prevent pressure from building up.
Exactly, in the receiver tank.
Step 3, and this is crucial, recheck for any signs of leaks in the system, particularly at fittings and joints. even if you just perform preventative checks.
Leaks are insidious. They can develop under specific load conditions. And finally, if all those physical components check out, the last step is to check the pressure switch.
So it could be a sensor issue.
It very well could be. It might require more than just adjusting. Sometimes the pressure transducer itself needs to be recalibrated or replaced. Sensors can drift over time, and report false lows.
The key here is that methodical, logical process. It's designed for speed. Now, let's contrast that with a truly complex fix. Question 4 asks the engineer to describe a challenging problem and its resolution. The source gives us a really high-stakes scenario. Excessive vibration was found in a rotary screw compressor, causing serious operational issues.
And this is where skills beyond those simple maintenance checks really kick in. Vibration is a symptom of deep mechanical distress.
So what did the engineer do?
The engineer here conducted a thorough inspection, likely using those vibration analysis tools we just discussed, which pointed not to a simple worn part, but to a structural issue. Misalignment of the drive shaft.
Wait, so even a small misalignment requires replacing the bearings? That seems like a massive consequence for a small error.
It is, and this really highlights the stakes. When a shaft is misaligned, even by minute tolerances, it induces immense axial and radial loads onto the bearings.
And bearings aren't designed for that.
Not at all. Bearings are precision components. They're designed to handle very specific forces. Excessive vibration heats them up, it degrades the lubricant film, and it leads to premature failure.
Which could seize the entire shaft.
Potentially. The consequence isn't just high repair costs, it's major operational downtime.
So the resolution involved 3 crucial steps: diagnosis, repair, and prevention. How was the misalignment actually diagnosed and corrected?
Well, diagnosis often involves specialized tools like laser alignment systems. They precisely measure the parallelism and offset between the motor shaft and the compressor shaft.
And a fix.
The engineer fixed the immediate problem by realigning the shaft using shims and precision adjustments. Then they addressed the consequence by replacing the worn-out bearings that had been damaged by all that stress.
And the crucial final layer, prevention.
Yes. They implemented long-term prevention. They established a regular laser alignment check as part of the preventative maintenance schedule.
To make sure it doesn't become a hidden killer again.
Exactly. This scenario shows a capacity for a complex diagnosis, for physics-based remediation, and for institutional process change. That's the definition of a high-level professional.
Yeah.
And in a technical field that affects everything from, automated assembly lines to air separation units, technology is just constantly evolving. Our final core question, Q6, addresses continuous learning.
Right. It asks, how do you stay updated with the latest developments in air compressor technology? And this demonstrates dedication to technological advancements, especially as industrial systems become more digitized and integrated into IoT networks. Static knowledge in this sector is simply obsolete.
That's absolutely right. The sources list 4 pillars of professional development. First, subscribing to relevant technical journals and magazines. That's where you find proprietary research on new lubricants, materials, efficiency gains.
Second, attending industry conferences and specialized webinars. That's where you see the cutting edge, like new variable frequency drive controls for energy optimization.
Third is participating in professional organizations. This is crucial for networking and for sharing those real-world problem-solving insights that you will not find in a textbook.
And finally, taking online courses and certifications to maintain their technical edge, especially in things like automation and control systems.
You have to.
This entire knowledge-based troubleshooting pressure, managing air-to-fuel ratios, proactive maintenance, it doesn't exist in a silo, does it? It feeds directly into a vast industrial ecosystem.
It connects to facility operations, power generation, specialized manufacturing. Mastering the air compressor is really mastering a central node of facility control.
Which is why the expertise feeds into roles far beyond just compressor engineer.
Exactly. Just look at the related jobs mentioned in our sources. This specialized knowledge is required for an air plant engineer, an auxiliary operator, a blowing engineer, a boiler engineer, even a building engineer.
So this skill set is really the lingua franca of facilities management.
It truly is.
So we successfully used these 6 foundational interview questions to efficiently distill the absolute core technical knowledge required in this field. We moved from understanding the functional differences between reciprocating, rotary screw, and centrifugal equipment, all the way to the scientific importance of the air-to-fuel ratio in combustion control.
We established that reliability is maintained through rigorous proactive routines, oil, filter, leak checks. And we analyzed the two tiers of troubleshooting,
The rapid systematic checklist for common low-pressure issues.
contrasted with the complex, expensive diagnosis required for those catastrophic mechanical failures, like tracking down that drive shaft misalignment using advanced diagnostics.
And this specialized technical knowledge is just critical for maintaining our infrastructure.
Indeed. We learned that something as specific as proper alignment or timely bearing replacement directly prevents massive operational failure. So, given that air compressors are vital components for diverse sectors like pharmaceuticals, where you need sterile air, and high-volume automotive manufacturing, consider this. How might a single, seemingly minor failure, point like that improperly aligned drive shaft, or a sensor reporting a false low-how, might that not only affect immediate operations, but also disrupt complex, just-in-time global supply chains? This knowledge isn't just about keeping a machine running, it's about ensuring global systemic reliability and the flow of commerce. It's something for you to mull over until our next deep dive.